All right, Antonio, already?
Yeah, sure.
Okay, so, very pleased to have Antonio Avilés López from Murcia and speaking on sequential octahedrality and L-orthogonal elements. Antonio?
Okay, thank you very much. I guess everybody's can see the slides now.
Yes.
Okay, so, well, first of all, I would like to thank Bunyamin for the kind invitation. It's for me a great pleasure to talk in this seminar. And I will present this work, sequential octahedrality and L-orthogonal elements. And it's a joint work with Gonzalo Martinez Cervantes and Abraham Rueda Zoca from University of Murcia, all of them now. Okay, so what am I going to talk about? I will start by showing you this. This is the beginning of a paper by Bernard Morey in '82 in this Longhorn Notes from University of Texas. And as you can see in this slide, his main result is that Banach space, separable Banach space E contains a subspace isomorphic to L1 if and only if there is an element in the bidual, non-zero element in the bidual that acts let's say that it's the norm of it when I add or subtract elements from the space is the same. And as it says, this statement is false for non-separable Banach spaces. Then he attributes the example to Hayden. Okay, so this is the Morey's statement, and well, I would add here a later result by Godefroy and Morey that we can this Morey's result characterizes the presence of L1 through an isometric property that talks about element in the bidual. And this condition 3 I added is something not about the norm itself of the space that contains L1. It says that a Banach space contains L1 if and only, separable Banach space contains L1 if and only if there is an equivalent norm that has a stronger property, that whenever I add, there is an element in the bidual, so that whenever I add this element of the bidual to elements of X, then I get it acts additively on elements of the space. Well, actually, Godefroy proved in '89 that the equivalence of 1 and 3, the characterization of a space containing L1, if and only if there is an equivalent norm of this sort, is actually true in any Banach space, not only separable. And in fact, when I say Godefroy and Morey, it's Godefroy itself in his paper in '89 that attributes the separable case to Morey as well. So these conditions are related to another condition that has become perhaps better known because of having a name, popular name, which is X being Banach space is octahedral. I wrote the definition of octahedrality here in the slide a little bit, well, not so precisely, but it says something similar to what we have above with elements of the bidual. But instead of comparing elements of X with elements of the bidual, we go to every finite dimensional space and we want to find an element out of it so that when I add up elements of the finite dimensional space with this element outside, the norm behaves as if it was L1, as if it was if I was adding a new coordinate to L1. In this definition of octahedrality that it doesn't call to the double dual, you need to put some epsilons to make it work. I'm not going to talk about octahedrality itself, but let me say that for a separable Banach space, this definition of octahedrality is actually equivalent to this condition 3 I have above for a norm in the space. that there is element in the bidual that the norm with when adding elements of X adds up. I may mention that it has been recently proved by Ginés López Pérez and Abraham Rueda Zoca that this is false for non-separable spaces. It's not exactly the same to have this element in the bidual or to have this octahedral condition. Okay, so this is first thing. An element view here. Okay, so an element of the bidual, let's put a name to the condition I was talking about. Let's say there's an element in the bidual, and let's assume that it has norm 1, just for fixing some, just for normalization. Is L-orthogonal if it has the condition we were talking about, that when I add this element to elements of X, the norm becomes additive. Example of such elements are, I mean, if you think of, for instance, of little 1, the dual of little 1 is L infinity, and the bidual are all the finitely additive measures on the natural numbers. And those which are L-orthogonal, the elements of the bidual of L1 that are L-orthogonal, are precisely those that are, as the name indicates, orthogonal to the measures that belong to L1, to the measures that are given by putting some weight on each natural number. So the L-orthogonal elements in little 1 are the finitely additive measures on the natural numbers that vanish on finite sets. And another example, just to get an idea of what's going on, is if you go to the Banach space of continuous functions on the interval 0, 1, and you take the difference of the characteristic functions of rationals and irrationals. So you take some function which is 1 on the rationals and -1 on the irrationals. Then this you can view it as an element of the bidual, because the dual of C01 are the measures, the Borel measures on C01, and I can integrate this kind of Borel function against each Borel measure, and it provides an element of the bidual. And because it's 1 and -1 everywhere, whenever I add this function to a continuous function, the norm will always increase by 1, because it doesn't matter. The point here is that the norm of a continuous function might be attained as as a positive or negative value. And in either case, if it is attained with a positive value, then the ones will allow me to make the norm a 1 unit up. And in the negative case, the -1 on the irrational will do the job. Okay. And here I just recalled the Godefroy's theorem that a Banach space contains little 1 if and only if there is some renorming of X that has an L-orthogonal element. And I'm going to consider in this talk another notion closely related to it. It's somehow implicitly considered by Moret in the paper I exposed at the beginning, and is that of an L-orthogonal sequence. So if I have a sequence of elements in the sphere of the space, I will say that this sequence is L-orthogonal if the limit, if it has the above condition, but on the limit of the ENs. So if I take an element X in the Banach space and I start adding the vectors of my sequence and I compute the norm, in the limit, it becomes additive. It becomes 1 plus the norm of X. Some examples of such things, if I try the same kind of spaces as above, simply the canonical basis of L1 has this property, because if I take an element of L1, it will eventually become very small. And when I have an element of L1, which after the 100 place, it's very small, then when I add vectors of the basis after 100, then the norm will increase almost by 1. And similarly, as before, if I now go to a space of continuous functions, if I take the Rademacher functions in the C01, or if you prefer, the coordinate functions on a cube, -1, 1 to the n, as I wrote there, they become, again, L-orthogonal. And the idea is similar as before with the rationals and the irrationals, because these functions have 1 and -1 in places, independent places. Any time I get a continuous function and I start adding these functions, the norm will eventually increase by 1, because I will eventually get both 1s and -1 very close to where the maximum of the function is attained. Okay, so this is example of L-orthogonal sequences. And actually, there is a result by Kadets, Szepelska, and Werner. They didn't use exactly this terminology of L-orthogonal sequences, but it's the same. And they proved that a similar theorem to Godefroy's holds for L-orthogonal sequences, meaning that a Banach space contains an isomorphic copy of L1 if and only if X can be renormed in such a way that there is an L-orthogonal sequence. Okay, so if we have, yes, if we have these two notions in front of us, the natural question is, what is the relation between one and the other? And the first observation is that I may have L-orthogonal elements without having L-orthogonal sequences, and the space where such phenomenon happens is what I wrote there, a C0 sum of uncountably many L1s, little L1s, because essentially there is an L-orthogonal element that will live in the L-infinity sum, which is the bidual, but it will be like an L-infinity element with uncountably many coordinates, and I will not be able to reach this element by a sequence. So in such a situation, I may have L-orthogonal elements without being able to reach them by L-orthogonal sequences. Actually, in this space, there are no L-orthogonal sequences at all. However, if I pose the converse implication, if I wonder whether, if I have an L-orthogonal sequence, can I get an L-orthogonal element? This becomes a more delicate question, and that's what I'm going to discuss. So let me, okay, I just keep the most essential information from previous slides. I have this question: if I have a space with L-orthogonal sequences, do I have L-orthogonal elements? The first observation that one can make is that this is true for separable Banach spaces, and this is essentially following what is written in this. This is the one follows the ideas from this original Moret's paper, where there is the origin of this theory, and one can get that for separable Banach spaces, it is true that if I have L-orthogonal sequences, then there are L-orthogonal elements. And while Abraham had these ideas, and he also realized that actually the proof can be with a little bit of set theory. Instead of separable Banach space, more or less the same arguments give that it's true for density of X less than cardinal T. And cardinal T is just some set theoretic cardinal, which is by some relatively recent and celebrated result equal to cardinal P. And all you may want to know about it is that you can define a cardinal that it's less or equal than the continuum, depending on what model of set theory you are. It may be equal to the continuum, or it may be strictly less. And well, it seemed that there was some set theoretic, let's say, ghosts around the problem. And so we started discussing it in Murcia, where there are some, let's say that we have some kind of ghostbuster tradition in this sense. And we wondered what happens for general Banach space X, no matter how big. And well, there is a natural guess because, okay, you have a sequence in the Banach space, in the sphere. Well, in the bidual, if I look at it in the bidual and I put in the bidual ball is compact and in the weak star topology. So this sequence has to have cluster points in the bidual, in the weak star topology. And perhaps the only thing you have to do is to take a weak star cluster point. And in the examples I presented before, this is how you, that's the relation between the examples I gave to you of L-orthogonal sequences and L-orthogonal elements, that the L-orthogonal elements were cluster points of the L-orthogonal sequences. And what we found is this fact, this is what I'm going to talk about now, that it's not true it's not true that if you take any cluster point, it's going to give an orthogonal element. And in fact, the following statement is independent of the usual axioms of set theory, that every L-orthogonal sequence has an L-orthogonal Wickster cluster point. So this is true in some models of set theory. This is false in other models of set theory. Okay, I will talk on it. So first of all, I need, wait a second. I forgot one thing, is that I have no, wait, just a minute. Okay, sorry. I forgot to have some place where to look at the time. So let me remind the notions of filter and ideal. This is something probably well known for most of you. An ideal is a family of subsets of, it could be any set, but let's think of the natural numbers that is closed under finite unions and subsets. So you may think that ideal is a family of sets that we may call small sets. If I have a set in the ideal, anything smaller is, and it's also closed under finite unions. And filter is the dual notion. It's closed, it's a family closed under finite intersections and supersets. If I have a set in the filter, then any bigger set, any set that contains the given one, is also in the filter. These two notions, as I said, are dual one of another. If I have a filter and I look at the complements of the elements of the filter, I get an ideal, and the other way around. So actually any notion that you define for filters can be thought in terms of ideals. And sometimes you may find definitions of the same concepts, either for filters or for ideals, depending on the author. Let me recall that a filter is an ultra filter if it selects from every set and its complement, it selects one of them. So whenever I get a partition of my set into two sets, one of them must belong to the ultra filter and the other doesn't, because it's not possible that both of them. And well, it's easy to see that if you combine this with the definition of filter itself, this is actually equivalent to say that the filter selects a set from every finite partition of the natural numbers. Whenever I make a finite partition of the natural numbers, one of them must be in the ultra filter whenever I fix an ultra filter. Well, the first example one gives of this are the principal ultra filters, which is just fixing a natural number n and taking every set that contains n. But as an application of Zorn's lemma, and therefore there's the axiom of choice behind. There are also non-principal ultrafilters, ultrafilters different from these ones. And well, this is quite a common tool that in Banach spaces and other areas, but it's very typical that people that use ultrafilters and perhaps are not specialists in set theory think of non-principal ultrafilters as that they are like all the same, that there is just the generic, that there is just an ultrafilter called U, non-principal ultrafilter called U, and there is no difference in choosing a kind of ultrafilter or of another. But this is something we will see in this talk, that sometimes it's not like this, that it quite depends on how the ultrafilter looks like, that you may get one behavior or another. Let me also recall the notion of limit of a sequence through a filter, or through an ideal, also sometimes written. And this means that whenever I take the X is the limit of Xn through F, if and only if, whenever I take a neighborhood of X, the indices of the sequence that fall in the neighborhood belong to the filter. If you take the filter consisting of all co-finite sets, all sets whose complement is finite, what you get is just the usual notion of convergence. So this filter notion means changing the notion of big subsequence. So for the usual convergence, the big subsequences are just the Q's of the sequence, and the Q's are what you have to insert into the neighborhoods of X. But if I have another notion of big set, then I have another notion of convergence, convergence through a given filter. And let me also recall that important that if K is compact space, then the limit through an ultrafilter always exists. So of course, limit through a filter as limit of a sequence might exist or not, depending on the sequence is convergent in that particular notion. But for ultrafilters, there is, if I am in a compact space, the limit through ultrafilter always exists. And actually, if I take a sequence, the closure of a sequence is exactly the same of all limits through ultrafilters. So it's, well, it's like a more general way of viewing all elements of a closure as limits of a sequence. You know that it's not always the case that you can get limits of sequence in the usual sense, but it's always
Antonio,
true that every...
Sorry about this. If you can hear me, maybe some students would follow and could get confused. What you mean about ultrafilter is A is in U if and only if n minus A is not in U, right?
Ah, yes,
this is not what's written on your slides. Sorry to bother you about this trifle, but...
Yes, this is a mistake, yes.
Sorry, Antonio.
Yes, one should write or another correction could be substitute if and only if by or. So, but yes, as I wrote it is a mistake. Thank you, Gilles. And finally, if instead of talking about the closure, I talk about the cluster points, the accumulation points, then these are the limits of the sequence through the non-principal ultrafilters. Because if you think of it, the limit through a principal ultrafilter, the limit of Xn through the ultrafilter UK is just the term Xk. It's just picking the corresponding element. So the non-principal ultrafilters gives the elements of the closure that are not in the closure for trivial reason, that are part of the sequence. Okay. So now that I have that, let me talk of what I was announcing, that not all ultrafilters, even not all non-principal ultrafilters look the same. We have, for instance, this notion. An ultrafilter is called a Q point if whenever I make a partition of the natural numbers into finite sets, well, I should say here non-empty finite sets. Sorry, I forgot to make the sets non-empty. For every partition into non-empty finite sets, there is an element of the ultrafilter that picks an element from each piece. So by choosing an element in each piece, I can create an element which is in the ultrafilter, meaning, as I told, one thinks of the ultrafilter as the big sets in some sense. So I can produce a big set by choosing an element from each piece. And we have another notion called selective ultrafilter. It's like a generalization of the previous one, where instead of, it's the same thing, but the partition is not into finite sets, it's just into sets that are not in the ultrafilter. Whenever I make a partition of points not in the ultrafilter, there is an element in the ultrafilter that picks one from each. Selective is more general because I'm assuming that these ultrafilters are non-principal, so they contain all cofinite sets. So, I mean, no finite set is in the ultrafilter, is what I mean. So, selective is more restrictive, yes, every selective ultrafilter is actually a Q point. And what can I say about this class as well? In some model subset theory, these are really, there are really the class of selective ultrafilters is non-empty. The class of Q points is non-empty and bigger, strictly larger than selective ultrafilters. And there are even ultrafilters that are not Q points. In fact, well, the fact that there are ultrafilters that are not Q points, this is true in general. This is always true. The point is that in some models there may be Q points or there may be no Q points. And that's what I said, that in fact one can find models of set theory where there are no Q points at all. So these are nice properties of ultrafilters, but well, the fact that one can really choose ultrafilters satisfying one properties or others or not depends on the model of set theory we're working with. Okay. So we go back to this how this problem about L-orthogonal sequences and L-orthogonal elements is related to this concept is that first theorem, if a sequence is if we have an L-orthogonal sequence and we take a limit through a selective ultrafilter, then that limit will be an L-orthogonal element. So remember what I was saying before, that the initial naive guess was take an L-orthogonal sequence, take a cluster point, and that should work. But a cluster point is in fact the limit through an ultrafilter. And what I'm saying in this first theorem is that if the ultrafilter is selective, if it has the property I said before, then that's true. Then in fact I get an L-orthogonal element. So in a model where there are such selective ultrafilters, every L-orthogonal sequence will have an L-orthogonal Wigster cluster point. On the other hand, the Theorem II says that there is an L-orthogonal sequence, says that when I take a limit through any ultrafilter which is not a Q point, then this will not be L-orthogonal. So what is the so what I'm saying, if I put the two things together, okay, start with an L-orthogonal sequence, if I take ultrafilter which is selective, I get an L-orthogonal element. If I take ultrafilter which is not Q point, I get an element which is not L-orthogonal. And we have some region in the middle, which are those ultrafilters, which are Q points, but not selective, where we are not sure what happens. Actually, we don't know. It would be nicer to have characterization, knowing, having an exact relation between how the ultrafilter is and the properties of the L-orthogonal element, but unfortunately, we are not able to make it so fine. But at least we know that in the two extremes of the chain of properties, we know that we get L-orthogonal or we get non-L-orthogonal. And as I wrote here, in particular, if I go to a model without Q points, in a model offset theory without Q points, as I mentioned before, that was first showed by Miller, there is an L-orthogonal sequence, none of whose weak store cluster points is an L-orthogonal element. So this settles the question of when weak store cluster points, of the independence, of the existence of the independence, that the Wigster cluster, whether the Wigster cluster points produce L-orthogonal elements. Another open question for us is, we have not been able to get a Banach space where in fact there are L-orthogonal elements, there are L-orthogonal sequences, but there are no L-orthogonal elements at all. We have not been able to push this machinery to kill all L-orthogonal elements, not only the weak star cluster points. Okay. And now I would like to give some ideas of what is behind the proofs of these two main theorems that make our main results by putting the two of them together. Let's start by talking about Theorem 1, meaning that the limit through selective ultrafilter gives L-orthogonal. And I will start reminding what an analytic set is. So one definition that it's usually written is that X is analytic. Let's say X is a topological space, for instance, or a metrizable space. Separable metrizable space is analytic if it is a continuous image of n to the n of the power set, countable power set of the natural numbers, which is actually the same as the rational numbers topologically. And we are interested in analytic ideals. So if I have an ideal is a family of subsets of n. And subsets of n are essentially the same thing as functions from n to the two set 0, 1, because I can identify its natural its subset of the natural numbers with its characteristic functions. I see that an ideal is analytic if, as a subspace of this counter set of this product 0, 1 to the n, it's an analytic set. It's an analytic space in the sense below. Well, the definition, the first definition I gave of analytic set is quite convenient, but this is not really the way in which you identify when you are given an ideal or a family, whether it is analytic or not. What you do is, okay, I give you an ideal and I describe when a set belongs to the ideal. And I try to write this definition in a logical terms, analyzing how many quantifiers I need to describe the set. And if I can write my belonging, A belongs to the ideal I can write it in the way there exists a real number X, such that for every rational Q1, there exists a rational Q2, such that for all. And I write how, no matter how many quantifiers over rationals. And in the end, I write a formula. And this formula is, in any reasonable sense, a continuous formula. And in Banach space theory, this is usually the case, that it comes from this family of natural numbers could come from this. Instead of the natural numbers, we could think of a sequence of a Banach space. And in the end, I may have some inequality with norms and some belonging of natural number to some sets. And if I can write my ideal belonging to my ideal in this way, then it will be analytic. And here, when I write, of course, when I write real number or rational number, it doesn't have to be exactly real numbers and rational numbers. Instead of rational numbers, I could use any countable set. Instead of the reals, I could put any anything which is canonically of size continuum, like branches of a tree, or subsets of n, or whatever. Set theory, it's usually called reals to anything like that. An ideal, another definition I need to put here is that an ideal is dense, or sometimes also called tall, if every infinite set contains an infinite subset from the ideal. So as I said before, you very often define an ideal by thinking of all the subsequences of a sequence, sufficiently small subsequences. And if I look at a class of subsequences with the property that every sequence contains a further subsequence with the property, this means that I am defining a tall ideal. Okay, and now I want to state Matthias theorem. It's a different characterization of selective ultrafilters. An ultrafilter is selective if and only if it intersects every dense analytic ideal. So in any way, I may define subsequences of a sequence. In a way that is nice, analytic means that I can define this family of subsequences in some reasonable way. And it's dense in the sense I said before, every subsequence have to have a further subsequence in the family. Then if I have this, every ultrafilter, every selective ultrafilter will contain sequences of this sort. Okay. So now this is just some photograph, again, some picture from Moray's paper. And I don't want to here try to make a real proof or arguments or things like this. I'm usually very bad at following proofs, and I try to give talks in the same way I'm able to hear them later. But simply, so Moray here is proving his theorems, and he defines some class of sequences. The sequence here where he fixed some epsilons here and some increasing sequence of finite sets he wants for this lemma, but he's defining a class of subsequences xn with a property that somewhere I corrected some mistake from the paper in red. That verify some small enough approximation of x plus xn plus 1 and x plus some linear combination of this xj. So in the end, well, I don't want to enter into the technical details. One has to make some modifications here, but the only thing I want to say is when Moray is proving his theorem, he defines certain class of sequences. And I didn't put it here, but there is another lemma or another part in the paper where he proves that every sequence of that sort contains a further subsequence with, every sequence contains a subsequence with a property given here. So this means that the subsequences that satisfy Moray's property, let's say, form a dense ideal. Well, perhaps not exactly the sequences that have the property, but the ideal that generates is dense. And well, I don't need to make many computations. When I see this definition here, I see for every sequence of positive real numbers that could be taken rational. And and there is some inequalities. In the end, if I read what is written here, I can write the kind of expression I wrote before with quantifiers over rationals and perhaps some quantifier over subsets of the natural numbers. and in the end, some inequalities with some norms. And this, in the end, means that the ideal I'm manipulating is an analytic ideal. So I have a dense analytic ideal where I can apply Mathias theorem. And it means that the sequences that Moret is considering here will meet my, my selective ultrafilter. And this means that this element in the double dual that in the end he claims to be to have the property that we are looking for to be L-orthogonal will be the limit through the ultrafilter, and that will finish the proof. So this is, as I said, running fast over the details, the idea of what's going on with Theorem 1, why in the limit through selective ultrafilter in fact gives L-orthogonal element. You just dive into the proofs and insert them into this set theoretic machinery, and it gives the result. Okay. Okay, sorry, I wrote here in the transparency the ideas I was mentioning. Okay, good. So now I want to give also some idea about Theorem 2. And remember, Theorem 2 was that what the Theorem 2 said, that if I have a sequence, that there exists some sequence, sorry. Remember, Theorem 2 was, there is a sequence, says that whenever I take a limit through non-Q point, then it's not an L-orthogonal element. And the first step is to find a different sequence for each ultrafilter I give you. So first thing what I do is I give you a non-Q point, and I produce a sequence where the limit through this non-Q point is non-orthogonal. And the second step is to glue all those sequences together to produce some big Banach space. Actually, it will have large density, as we should expect from the observations I made at the beginning, where the above condition will work for all non-Q points at the same time. Okay, well, I will not talk about the second step. So this is the second step will be just well, adding a lot of extra coordinates where to put it. I mean, how to glue the sequences together. But I want to talk a little bit about the first step, because I think there are some ideas I want to highlight. So what we are doing, what are we going to do? So we start with a non-Q point. And remember what it means, non-Q point. Non-Q point means that I can take a partition of the natural numbers into finite sets without selections in U. It's because it's not Q point, it is impossible to pick an element from each set of the partition and produce an element of the ultrafilter. Okay, so now once I have this, I can consider this filter, which is all the subsets of the natural numbers, says that when I remove A from each piece, I get a uniformly bounded sequence of cardinalities. So this set is contained in U. Why? Because if some set of this form was not in U, then the complement would be in U. And the complement would be what? The complement would be picking a uniformly bounded number of elements on each piece of the partition. But if that would be an element of U, then, well, I could decompose this into finitely many pieces, such that each of them would be selection of one element in each element of the partition. And then I could pick one element in each piece and be in the ultrafilter, and that's impossible because I'm not Q-point. So, well, I just take this filter, which is now contained in U, and what I'm going to do, well, once I have ultrafilter which is not Q-point, in fact, instead of working with the ultrafilter, I will work with this smaller filter that already captures the essence of the fact that U is non-Q-point. I also consider the compact space of sequences of -1s and 1s. So this is like a subspace, this is a closed subspace of a Cantor set. And this is made of all, actually, of all these selections. It's the characteristic functions of selecting one point, at most one point in each element of the partition. So this gives me a compact space K, subset of the Cantor set. And well, because these are -1s and 1s, and while it's an exercise to notice that this K doesn't have isolated points, in the end, this sequence will look very much like the Rademacher functions that I mentioned at the beginning, that they are an L-orthogonal sequence. So what I have here is just like a version of the Rademacher functions, but just adapted to the context where I have this partition. And well, the observation is that if I take the sequence of the limit, sorry, of this sequence, of this L-orthogonal sequence through the filter F, this gives the constant function equal to 1. This is just because of the definition of K, because what I need to prove is that if I fix, all the elements, all the characteristic functions are from elements which are actually in the complement of F. So I will. Okay, I don't want to make computations here, but this is a fact. This is just from the definition of K and the definition of F. The limit through this filter is the constant function equal to 1. And actually, this is an example here, just like this, of a sequence where this is L-orthogonal sequence, but I am taking certain limits through a filter. I'm taking, so therefore, a cluster point, and this cluster point is not L-orthogonal because the constant function equal to 1 is not L-orthogonal. I need to have this Rademacher behavior. I mean, I need to have a lot of 1s and -1s everywhere to get something that is L-orthogonal. But now, I have the pointwise limit of En is 1. This is just a matter of playing with the definitions. But what I would like to have is that the weak limit of F is the constant function equal to 1. Because, well, this is an exercise. If the limit through a filter is 1, then the limit through a bigger ultrafilter is also 1. That is simple. I mean, if I make bigger filter, I preserve the convergence. And then what I would have what I want. I would have the limit through my non-selective ultrafilter being non-L-orthogonal. So what is the problem here? The problem here is that I need to go from pointwise convergence in the CK space to weak convergence. And to do this, what do you need to go from pointwise convergence to weak convergence? You need the Lebesgue-dominated convergence theorem, because weak convergence means converging over each element of the dual of C of K. But the dual of C of K are the measures. So what I need is that whenever I take a measure on K, the integrals with respect to that measure need to converge to the integral of the pointwise limit. So I need a Lebesgue-dominated convergence theorem, but instead that for usual convergence of sequences, for convergence through this filter. Now, this kind of question, when Lebesgue-dominated convergence theorem works for filter convergence, has been considered by Vladimir Kadets and Leonov. Kadets and Leonov, they actually give that a name. They call a filter that satisfies that property. They call it Lebesgue filter. But unfortunately, unfortunately, I mean, the kind of filters they consider in their work are variations of the so-called statistical convergence filter. But this filter we have here, this F, is not exactly of that form. So we cannot use the results. So we need to actually prove that for this, for this filter F, the dominated Lebesgue convergence theorem works. And I would like to finish my talk by mentioning that, well, in order to prove this Lebesgue dominated convergence theorem, we need this this measure theoretic lemma. And well, I just stated here in case perhaps, because this looks like, well, something that perhaps is known from some other context from measure theory. So perhaps somebody may recognize it and tell us, oh yes, that's from, you can find in that book or in that paper in that context. So the lemma says that I have here the formal statement, but let me write here in blue, just like in words. In a sufficiently large family of sets of measure epsilon, the intersections of n many sets cover more than measure epsilon prime. So whenever I fix a smaller epsilon prime than epsilon. Okay, so that's all. Thank you very much. This is the end of the talk. Thank you.
Right. Thank you so much, Antonio. Questions?
Yes, thank you, Antonio, for this very nice lecture. I mean, I will probably send you a message actually to asking a few questions, some comments, but just to make it short, first of all, I mean, it's great that you advertise this remarkable work by Moret that was just published in a seminar, and it's a really deep paper. I wanted to mention that in the special case of subspaces of weakly sequentially complete Avilés, there is a more elementary proof which was provided by Yamina Yacoub-Zidi a few years ago. It's published in a paper in Mediterranean Journal of Math. So in a special case, but which is quite important in applications, there is a simplified approach to Moret's theorem. And maybe that could be useful also in that specific context you consider. So I don't know if you are aware of the paper, but it's not a very known name. So I wanted to attract your attention and the audience attention on this paper by Yamina Yacoub-Zidi. Now, maybe a question which is related with what you mentioned as an open question in your lecture, that is, you have a Banach space X with an L-orthogonal sequence and no L1 type in Moret's terminology in the bidual at all. There is one open question in the paper with Nigel Carlton in the ball topology, which I think is still open. Maybe this should be checked. If you have a space X so that the bidual unit ball is Hausdorff for the ball topology, does this imply that X cannot contain little L1? Okay, that is, in the ball topology, we show that if X does not contain little L1, the bidual ball is always, if X does not contain little L1, the bidual unit ball is always Hausdorff for the ball topology, but we don't know about the converse in full generality. It's an open question in the paper, and I believe it's still open. Do you have any opinion about this?
So you said this is from the paper with Carlton, you said?
That's right. It was a ball topology paper. I mean, paper back from 86, actually.
Okay, well, I don't know.
That is, if we know that every space, okay, it's a little bit involved question, so probably I will remind you in my message about this. But if that would be a strong dichotomy for spaces containing or not little L1, a strong isometric dichotomy, which is related with Moret's theorem, but we didn't know the answer at the time, I believe, but please check before working on it if you wish. I believe it's still open today. Okay, it's also related with the work by López and Johann Langemetz about the bidual octahedral norms. Okay, the recent progress they managed to achieve. Okay, but this ball topology question could be related with the open question you put in your lecture.
Okay, thank you.
Okay, you're welcome, Antonio, and sorry for having been so long for the whole audience.
Any other comments or questions?
Yes, maybe in relation with the comment, the Gilles comment, I recall this problem and the difficulty, in my opinion, is that when you start with a Banach space containing some L1 copy, and you want to prove something in the bidual around ball topology for every equivalent norm. So some, if I'm not wrong, so maybe some more specific question is if you assume that your L sequence is isomorphic to L1, you can get something extra condition in the limit.
Well, I believe that L-orthogonal sequence, I think it has to be isomorphic to L1, doesn't it? Or I'm confusing something now. Abraham, am I right? I mean, it has to be isomorphic to L1 or...
Yes. It should contain subsequences which are 1 plus epsilon isometric indeed.
Okay.
I say so if it's isomorphic to one basic sequence, you can get something extra in the limit around the norm, some kind of behavior, or maybe not.
I don't know if there is some. I don't know.
Okay, thank you.
Okay. Thanks again, Antonio. So we can, of course, continue our conversation. I'll stop recording now.